Hi, I'm Xiaoming from Southwest Jiaotong University. We are glad to present boosting single image super resolution via partial channel shifting for SR community. Single image super resolution is a fundamental topic in low-level vision that focuses on restoring a high-resolution image from a low-resolution counterpart. In recent years, deep learning has greatly advanced the development of SISR, pushing its performance to a very high level. However, it still hit the bottleneck with a larger model size and overwhelmingly computational cost. Therefore, the objective of this study is to introduce a simple approach called partial channel shifting to enhance the performance of SISR, which aims to improve SISR without the need for additional parameters. Temporal shifting has demonstrated high effectiveness in video understanding by shifting a portion of the integral feature channel along the temporal dimension. Taking inspiration from this concept, partial channel shifting involves a slight displacement of a portion of the feature channel along the channel dimension. This displacement effectively expands the receptive field and enhances feature diversity. The shifting operation directly truncates the elements that are removed, with the truncated features simply padded with 0 to maintain the original dimension. Our intuition is that convolution benefits from incorporating shifted features. By including the additional local information during each calculation, the receptive field of a convolution will be effectively augmented. However, regulating the features with PCS poses certain challenges, such as determining the shifting direction and amplitude, maintaining appropriate proportion, and managing patterns of the shifted channels. Upon analyze, we identify 4 major challenges associated with PCS. Firstly, employing excessively large shifted magnitude can disrupt the locality of the SISR, thereby degrading its performance. Secondly, the loss of boundary information during the shifting process hinder pixel-level recovery. Thirdly, data movement introduces implications for inference efficiency. Lastly, considering the various combinations of shifted patterns become impractical to exhaust comprehensively. To address this dilemma, we propose several technique constraints that require decision-making. These constraints include determining the shifting magnitude, choosing which channel to shift, and deciding the permutation of shifted and unshifted channels. For our experiments, we select two off-the-shelf SISR models as baseline models, DRRN and EDSR. DRRN is a lightweight recurrent model, while EDSR is a residual middle-scale model. We conduct the following experiments using these models. Next, we perform a series of ablation studies to examine this constraint. Firstly, we conduct an experiment on shifting directions. The spatial-wise direction contains 8 main directions, including horizontal, vertical, and their diagonal. We enumerate different combinations of shifting direction and found the performance of SISR is not significantly sensitive to the specific shifting direction utilized. We then conduct experiments on the permutation of shifted and unshifted channel. After clustering them into various groups, we observed no significant difference among these permutations. As a result, we opt for the simplest permutation where the shifted channels are centered. After analyze, we identified 4 shifted patterns that encompass a wide range of shifting patterns. These patterns include unidirectional, bidirectional, cross-directional, and quad-directional shifting. Following that, we conduct experiments on the proportion of shifted channels using the 4 identified shifted patterns. The figure below illustrates the vanilla shifting settings with the typical shifting patterns along with their corresponding latency. Interestingly, our observation contradicted initial intuition. For instance, the bidirectional shifting, covering only 2 directions, exhibit better performance compared to the octadirectional shift, which covered 8 directions. However, it is worth noting that the latter incurred high latency overhead. Lastly, we applied the empirical determine the optimal settings to enhance the performance of 10 off-the-shelf SISR models. These models exhibit varying level of improvement. Taking EDSR as an example, we observed a maximum gain of 0.18 dB when employing self-ensemble strategies. Additionally, we utilized Analyze tool to assess the impact of PCS on the SISR model, including evaluating the effective receptive field and the local attribute map. The visualization of ERF demonstrated that the receptive field expands as shifting directions are incorporated. Local attribute map further indicate that the PCS enhanced model can effectively utilize additional information, resulting in improved spatial correlates and texture consistency in the output. Partial channel shifting is an effective strategy to enhance the performance of SISR without introducing extra parameter or flops. However, it relies on the cooperation of residual connection and the use of identity mapping, which are essential for restoring the shifted features. Furthermore, compared to directly increasing long-range dependencies, improving local feature correlation is also an effective approach in the context of SISR. Thank you very much.